Thank you, and thank you very much to the organizers for giving me a chance to talk in this wonderful workshop. So, what I'm going to present was obtained in several works. It started with Erwan Faou and Zahir Hani. Then there is another work that I did with Zahir Hani and Laurent Thoman. There is still another work in collaboration with Patrick Gérard and Laurent Thoman. And finally, the more random aspects are joined with Isabelle Gallagher and Zahir Hani. Okay, so the idea is to start with 2D NLS. On the torus. But then I'm going to introduce a small parameter, epsilon squared, and a large parameter, L, so that now the torus has size capital L. And the plan is to let epsilon go to 0, which amounts to the weakly nonlinear regime, and L go to infinity, which is the big box limit. And then we'll see that many interesting things happen. So, though what I'm going to present is about this particular equation in this particular geometry, you can, of course, ask the same question for any nonlinear dispersive PDE in any geometry. Take the same limit and see what happens. Okay, so these works are related to the idea of weak turbulence. So to put it in vague terms, it is the belief that the typical solution of this equation, as time goes by, is going to try and move energy towards high frequencies. And of course, it can do so only as much as it is allowed by the conserved quantities. So energy moves towards high frequencies. So this idea was first put forward by physicists, but let me start by discussing the mathematical approach. So the idea is that if indeed energy moves towards high frequencies, then U of t in Hs with S sufficiently big, say S equals 10, should grow as t goes to infinity. And I should put a question mark. So what is known, so somehow the conjecture is that generically this happens. So what is actually known is an upper bound, which is due to Bourgain and then was improved by Stafilani, which says that U of t in Hs cannot grow any faster than polynomially. Okay. And as far as lower bound goes, the best result as of today is due to the IT, Colliander, Kiel, Stafilani, Takaoka, and Tao. who showed that for any, say, delta and capital M, there exists a solution U and a time capital T such that U at time 0 in HS is less than delta, and U at time T in HS is bigger than M. So you can go? Oh, yes, sure. So there is solutions that go from arbitrarily small to arbitrarily large in the HS topology. But though this behavior is expected to be generic, there is no single example which is known where this growth actually happens as t goes to infinity. There is an interesting recent result due to, so let me get it right, Hani, Posader, Dishilia, and Tsvetkov, who show that U of t in HS goes to infinity as t goes to infinity for a certain solution U, but then you have to set the equation on T2 cross R. Oh, okay, thank you. Okay. All right, so as you see, our knowledge is very lacunary, since though this is expected to be generic, there is no single example known where this happens. Okay, so that was for the mathematical point of view. Now, how did physicists think of this problem? Okay. So if you open a physics textbook on this subject, you see that physicists believe that the right regime to consider is the following. So first you send epsilon to 0, as above. Then you send L to infinity. But then you need to assume that there is some randomness, namely that the phases of the Fourier coefficients of U are statistically independent. And this is known as the random phase approximation. Okay, and so the statement is a bit vague, but as it appears in physics textbooks, it is a bit vague. Okay, so under these three assumptions, in physics textbook, there is an equation which is derived. Then you derive an equation on the expectation with respect to this statistical distribution of phases of bk squared, where the bk are the Fourier coefficients of U. And this equation is known in the Russian literature as the Kolmogorov-Zakharov equation. And in the American literature, sometimes as the kinetic wave equation. And there was recently a very nice result by Escobedo and Velasquez, who were able to describe fairly precisely the asymptotic behavior of this equation, in the case of radial data. But there is a big problem with this equation, is that there is no rigorous derivation known. Okay. So what I'm going to present today is first examine this regime where you let only epsilon go to 0 and L go to infinity, and then examine another regime where these two things happen and we put some randomness in a way that I'm going to describe. And then in these two setups, we are able to derive new equations. I mean, a new equation if you just take these two assumptions. And if you take these two plus an appropriate randomization, we are able to derive the Kolmogorov-Zaharov or the kinetic wave equation. Okay. So I'm going to start with the deterministic setting. One, the deterministic setting. Okay, so we start with a solution U of this equation on the L-dimensional torus. And then we prescribe data. So the data are fixed, but the size of the torus is growing. So you can think of the data as having, say, compact support, and then the torus is getting bigger and bigger. Okay, and then we want to let epsilon go to 0, L to infinity, and get a new equation. So the first step is classical. It's just to filter by the linear evolution, which is a good idea since we are in the weakly nonlinear regime, and then view things in Fourier. So in other words, you write U as the sum of the bk of t, e I kx plus t k squared. There is some normalization that I don't care about. And here k is living in the dual Fourier space, which is z over L squared. So for instance, if I take epsilon equal to 0, the bk are constant, and you just get a linear solution. Okay, so now let us write the equation one obtains on bk. So NLS on bk becomes bk dot equals, so it's a small computation, the sum over k plus L equals m plus n, bl bar, bm, bn, e to the it omega, where omega equals k squared plus L squared minus m squared plus n squared. And there is an epsilon squared. Okay, so it's just a small computation. You see that NLS becomes this equation when you look at it in the bk coordinates. Now, the basic idea is that epsilon is very small, so bk dot is very small. So bk is evolving very slowly. On the other hand, if omega is not 0, here you have some oscillation in time. So as long as omega is not 0, this guy is going to oscillate. These ones are almost constant. So the effect on bk should be essentially 0. So this just amounts to making a normal form transform. And if you believe in what I said, the dynamics of this equation is well approximated by the resonance system, which reads bk dot equals epsilon squared sum over k plus L equals m plus n, and omega equals 0. Yeah, I'll raise it in a second. BL, BM, BN bar. Right. Okay, so we started with NLS. We look at it in the BK coordinates, and then we reduce to resonant interactions for which omega is 0. Okay, so this is where we use the smallness of epsilon. Now we don't care about epsilon, and we just need to let L go to infinity. All right, so we managed to reduce matters to the equation. Okay, so I forgot an I. The right equation is I bk dot equals epsilon squared sum k plus L equals m plus n, k squared plus L squared equals m squared plus n squared, BL. Okay, and this is the resonance condition. All right, so now what do the tuples K, L, M, N look like which satisfy these two relations? Well, it's a simple exercise to see that K, L, M, and N are resonant if and only if they are arranged as a rectangle. So if I take capital L equals 1, I draw the Fourier space. So this is Z squared. And if I want to understand this system, I need to find all the rectangles in Z squared. So there is quite a few. And you need to solve a small arithmetical problem to find them. It's not very hard. Now, the advantage is that if L is very big, the lattice is becoming or the mesh is becoming very fine, if you want. And I don't care so much about finding rectangles exactly. What I want is only finding a density of rectangles. And this becomes very simple. So here I can simply look at the density of rectangles. In other words, if I take x, y, z, t in R squared, which are arranged as a rectangle, I can look at all the k, l, m, n in z over L squared to the 4, such that K, L, M, N is a rectangle, and K, L, M, N is close to x, y, z, t, say, minus x, y, z, t is less than delta. So I can look at this set, and the good news is that it has the size of this set has a limit as L goes to infinity. But this is natural if you look at the picture, right? Since the lattice is becoming very fine, you can find sort of statistically rectangles. So the right normalization is to divide by L squared log L. And then this converges as L goes to infinity to some limit. Okay. So at this point, perhaps it's good to have in mind a small analogy. So we have this sum here, and we know about the density of we know about the density of the KLMN which satisfy this relation. So I'm going to argue that this is very much the same thing as a Riemann sum, except it's a bit more nonlinear. So the classical thing is that, whoops, if phi is a smooth function, then if you take the sum over k in z over L, say, of phi of k, you normalize, then this converges to the integral of phi dx. Okay. So what I'm saying is that this is exactly the same situation here, except it's a bit more nonlinear. So for us, if you think of BL as phi of L, where phi is a smooth function, then you can take exactly the same limit in this sum and go from a discrete sum to an integral operator. Then the sum over all resonant contributions of phi of L, phi of M, phi of N converges to an integral operator. Okay, so here it depends on k, so here it depends on k. And you need to normalize by dividing by L squared log L. Okay. So with this in mind, we're going to be able to pass the limit in this equation and find PDE on phi. Okay. Okay, so let's do that. So we start with I bk dot equals epsilon squared sum over all the resonant contributions of BL, BM, BM bar. And then you think of bk as phi of k, where phi is a smooth function, and you're taking the trace of this smooth function on z over L squared. Okay, so you do that, and well, the left-hand side obviously converges to I phi dot, and I'm going to call x the continuous variable. And then the right-hand side converges to this integral operator that I discussed over there, which is, I'm going to call t of phi of x. Okay. So that's the equation that you find. And I need to tell you what t is. So it's actually fairly natural. You find that t of, say, f, g, h of x. You can view it as an integral of f of y, g of z, h of t, and then x, y, z, t have to satisfy the two relations above. Right? You put delta of x plus y minus z minus t, delta of x squared plus y squared minus d squared minus t squared, dy, dz, dt. So this is pretty much expected, right? Given that we had these two relations at the discrete level. Then what's less clear is that you don't have a density here, but you do the computation, there is no density. And there is a bar on the first one. Okay, so that's the equation we find, and that's the integral operator that appears on the right-hand side. So, okay, so I'm going to write a more rigorous statement. So, Fau and Hani. So, you let U solve NLS. You let G solve this new equation. Okay. Then if epsilon goes to 0, L goes to infinity, and epsilon L goes to 0, under these three conditions, BK, so BK is the thing that I've denoted BK up there, which comes from the Fourier coefficients of U. So BK of T star T minus G of TK in L infinity is less than a constant divided by log L. And T, say you can take it between 0 and 1, but actually so there is a more refined statement that I'm not going to write down, but where you see the dynamics of G over arbitrarily long times. Okay, so, oh, sorry, thank you. So T star, I'm going to write it here, T star is L squared epsilon minus 2 log L to the minus 1. Okay, so that's the new equation. So I think it had not appeared before. So now what I'd like to do is discuss a little bit its properties. Sorry? Oh, sorry. Yeah, the two equations. So the data of. Yeah, let me write it down. So U naught hat of K equals G of K. And G is, say, C0 infinity. But it's possible to do better. U0 hat of K is G0 of K. Okay, so I think the optimal assumption is that G, okay, so x squared times G is bounded in L infinity, and the same holds for one derivative of G. I don't know if it's optimal, but it's the best we could do. Okay, so now, what about the properties? Okay, so first, it's easy to see that this equation is locally well posed and globally well posed in L2. The next thing is that it has a Hamiltonian structure, and it actually derives from the Hamiltonian h of G equals so the Hamiltonian of the system is exactly the L4 Strickhart's norm. Right, so here G, maybe I shouldn't call it G, say F. So F lives in R squared. You take the Strickhart's norm. Okay, so, but there is a confusion which comes from the following fact, which is that this equation is invariant by taking the Fourier transform. And actually, this h of f equals h of f hat. Okay, so this is all very weird, right? But there is more. It actually turns out that T of GGG is exactly the resonant sum, or if you want, the resonant part of the nonlinearity for the equation, so the Schrödinger equation, with harmonic potential. Okay. So it's exactly the resonant sum. You don't need to take a big box limit. Okay. So it actually raises the question of how universal this equation is. Yes? Right, focusing, defocusing doesn't matter. No, it still doesn't. It's all somehow in the weakly nonlinear regime, so you don't really see the size of the... So, okay, this raises the question of how universal this limiting equation is. Namely, what I presented is taking a data on a torus that becomes bigger and bigger. Then you get this equation. If you do the same in a potential well, you don't even need to let it become bigger and bigger. You get the same equation. Now, what if you take, some out of geometry? You put the data on a sphere, and you let the sphere grow. Do you find the same equation? I'm tempted to believe that you do. But in even, in situations where you don't have any symmetry at all, I don't know. It would be very interesting to understand. But this universality is somehow natural relatively when you look at the Hamiltonian, right? The Hamiltonian only sees r squared, right? So it doesn't see much from the original geometry. Okay, so this is pretty open. Sorry? Yeah, indeed. Here, you don't need to let L go to infinity, right? But probably the power of L depends on the geometry. Okay, so there is another very striking property, which is if you consider special Hermite functions. So the special Hermite functions, they are eigenfunctions of the harmonic oscillator and the rotation operator. Okay. So you can, let's call them CKL, and K is going to be the eigenvalue of the harmonic oscillator, L the eigenvalue of the rotation operator. It turns out that T of C K1 L1, C K2 L2, C K3 L3 is C K1 plus K2 minus K3, depending where you put the bar, L1 plus L2 minus L3 times the coefficients. Okay, so this gives a lot of invariant subspaces, and in particular, any special Hermite function is a stationary wave of this equation. So, okay, so this we discovered with in the paper with Laurent, and then talking with Patrick, he noticed that a particular subset which is invariant is provided by the span of z to the n e to the minus z squared over 2, where n is an integer. Okay, where I use a complex notation which is pretty clear. But this is exactly the set of functions which, so the span in L2, with the functions of the form e to the minus z squared over 2 times holomorphic, which is known as the Fock Bargmann space. And on this invariant subspace, the Hamiltonian becomes integral of u to the 4 dx. So at this point, you notice two things. First, this is extremely reminiscent of the Segue equation. So the Segue equation is the same Hamiltonian, and on a set which also involves spaces of analytic functions. And second, this corresponds to a model which is well known, which is called the lowest Landau level, which has been studied more from a variational point of view, but which appears here naturally. I mean, so the Hamiltonian dynamics of this model are contained in this equation. Okay, so of course the question that one is tempted to ask is whether this equation, or perhaps this restricted equation, is completely integrable, and so far we don't know, but might well be the case. Okay, and so there is many other very striking properties that I don't have time to discuss, because I would like to say a few words about the randomized setting. Okay, so now what about the randomized? So what I'm going to discuss now is work in progress. We already have a result, but it involves an a priori assumption, and this is joint with Isabel Gallagher and Zahir Hani. Okay, so recall that U is the sum of bk ei kx squared and as I mentioned at the beginning, the regime that physicists like to look at is the regime where epsilon goes to 0, L goes to infinity, and there is this random phase approximation So what I'd like to do first is to explain what is the basic problem with the random phase approximation. Okay, so what you would like is an equation on phi k, which is the expectation of bk squared. And the expectation being taken with respect to this statistical ensemble where phases are supposed to be independent. Okay, now let's be naive and assume that bk can be written modulus of bk times ei theta k, where the theta k are statistically independent at each time, and yes, so say let's assume that they are uniformly distributed on 0 to pi. Okay. So then if you assume that and you do a small computation, you see that dt phi k equals so the time derivative of the expectation of bk squared okay, so it's twice the real part of the expectation of bk bar times the resonance sum of bl, bm, bn bar. So if I put back so here there is an epsilon squared and there is an I. If I put back the phases, I get real part expectation I bk, bl, bn, bn, ei theta k plus theta l minus theta m minus theta n. And you see that this is 0 because you're taking the expectation of this thing, unless this sum is identically 0, but then you're taking the real part of something which is purely imaginary, so this is 0. Okay, so I cheated a bit, but because, for instance, you could assume that the theta k and the bk are correlated in a complicated way. Okay, but at least if you do the naive thing, you immediately see that there is a problem. Namely, if the phases are really like that, then nothing moves, at least on average, right? But the good news is that if you look at the second time derivative, the second time derivative under this same assumption gives something which is non-zero. So you do the same computation, and what you find is the sum over the resonance set of phi L, phi k, phi L, phi n, 1 over phi k, 1 over phi L, minus 1 over phi n, minus 1 over phi n. Okay, so it's a small computation which is not hard, pretty much like that. Okay, so you see two things. First, this random phase approximation, at least naively understood, is not good because then nothing evolves, right? But on the other side, as soon as you have the random phase approximation, the second time derivative of phi k is not 0. So if the random phase approximation is satisfied at one point in time, then it immediately so correlations immediately appear as time goes by. Okay. Sorry? No expected value. Okay, and I also cheated a little bit here in that I assumed that the bk were decorrelated in order to commute the expected value with the. Okay. So what we did in order to take this problem into account, so if you want, the big question is, first, how to understand the random phase approximation, and second, somehow, what is the mechanism which is responsible for the phases being decorrelated? Right? So why are phases decorrelated? Okay. So we decided to help nature a little bit by making the phases decorrelated by hand. So let me explain that. So the right. Okay, so the system that we consider is the following. you solve NLS. And you do so on all the intervals of the type n tau, n plus 1 tau, where tau is a new parameter and n is an integer. Then at time n tau, what you do is you randomize phases. So namely, you let bk of n tau plus equals bk of n tau minus times exponential I theta kn, where the theta kn are IID random variables uniformly distributed in 0 to pi. So you can think of it as a random forcing, but of a particular type. It's only forcing the phases. So if you want, in the absence, since we don't really understand what is the mechanism which makes the phases decorrelated, we help them being decorrelated. Okay, and then from this system, if you let epsilon go to 0, L go to infinity, and tau go to 0, so this corresponds to the weak nonlinear limit. This is the big box limit, and this is the random phase approximation. So if you take these three limits, from this system, we can derive the Kolmogorov-Zaharoff equation. So I don't have much time, so let me be very quick. First, epsilon go to 0. Okay, so this we understand well. It's going from NLS to the resonance system, just like in the deterministic case. Okay, easy enough. Next, oops, sorry. I mean, in the end, the order doesn't matter, but for explanatory purposes, I'm gonna first let tau go to 0. Okay, and then as tau goes to 0, what happens is that, okay, so I don't really have time to explain, but you go from a second order in time system to a first order in time system. So the equation you get is dt phi k is the sum over resonance of phi k, phi l, phi m, phi n, 1 over phi k, 1 over phi m, 1 over phi n, 1 okay, so modulo rescaling in time. And there is an error term here. And finally, you let L go to infinity. So as L goes to infinity, just like in the discrete case, this converges to the integral operator, which is the one appearing in the Kolmogorov-Zaharoff equation, and the error goes to 0. There is just a little problem in this derivation. It is that in writing that, I have assumed that the bk squared, the moduli, are decorrelated. But actually, they are not decorrelated. As time goes by, they correlate. And so what we need to do is run something which was introduced by Lanford to derive the Boltzmann equation. Namely, we need to write an equation, hierarchy of equations on quantities of this type. Okay, so we need to write a hierarchy of equations and then prove that take the same limit and then prove that the hierarchy you get in the end has a single solution which is given by a tensor product, so just like for Boltzmann. And this concludes my talk. Thank you for your attention. It's pretty likely, yeah. I mean, we don't really have a reason for this invariant.
Is your final PE,
yeah.
final equation,
Yeah. Okay, so this I don't know. It's well known that the L4 Strickhart's norm is invariant by taking the Fourier transform, right?
Right. You think that's the base, which is the solution.
Okay. So I mean, but do you have a precise way of seeing it? I mean, I understood it in a more like sort of spiritual way, but there is actually there is a rigorous link between the two. Okay. No, it's like you do a normal form transform, right? So I was a bit sloppy, right? But if you want, epsilon being small enables us to replace the NLS system by the resonance system. But indeed, it doesn't quite reach 0. Right, and that comes from this. I can explain to you easily on a simple example. So suppose we look at an ODE, which is f dot equals 0 at the time n tau, f double dot equals capital F at the time n tau, where n is an integer, divided by tau, and f triple dot is bounded, say, for all t. It's not hard to see that the solution of this equation, of this ODE, converges to the solution of f dot equals capital F. So here it's exactly the same. As tau goes to 0.